Hello there, and welcome to my channel. I'm so glad you found your way here tonight. Whether you're nestled under warm blankets, curled up on the couch with a cup of tea, or simply winding down after a long day of being wonderfully human, you've come to exactly the right place. This is our quiet corner of the universe where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we're embarking on a gentle voyage beyond our solar system, drifting through the cosmos to explore one of the most captivating questions humanity has ever asked. Are we alone? We'll be searching for exoplanets, those distant alien worlds that orbit stars far from our sun. It's a journey filled with ingenious detective work, revolutionary discoveries, and perhaps most remarkably, thousands upon thousands of worlds we never knew existed. Before we begin our cosmic wandering, I'd love to know where in the world you're listening from tonight. Are you watching from a bedroom in Barcelona as the clock strikes midnight? Perhaps you're settling in from a living room in Tokyo while the city hums softly outside. Or maybe you're drifting off in Denver, watching the last light fade from the mountains. Drop a comment and let me know. It's always such a joy to see this sleepy community scattered gently across time zones and continents. If you find these peaceful explorations through science helpful for unwinding, whether they carry you off to dreamland or simply offer your mind a quiet place to rest, I'd be ever so grateful if you gave the video a like and perhaps tap that subscribe button. It helps more fellow wanderers find their way to these starlit stories. Now, I do hope this video isn't too fascinating. After all, we're here to relax, not to lie awake pondering the vastness of space. But if you do find yourself still alert by the time we discover our first alien sunset, well, at least you'll have learned something extraordinary about the universe we inhabit. Sometimes the most beautiful way to fall asleep is to the gentle rhythm of cosmic wonder. So settle in, take a deep breath, and let your thoughts drift as we begin. Somewhere out there, beyond the familiar glow of our sun, beyond the comfortable boundaries of our solar system, entire worlds are spinning quietly in the darkness. Some are scorched by radiation, others frozen in perpetual winter. Some might have oceans deeper than any on Earth, while others could have skies filled with colors we've never imagined. Tonight we're going to discover how we find these hidden worlds, what they might be like, and why their existence fills us with such profound wonder. It's a story that begins not with rockets or telescopes pointing skyward, but with a simple, almost childlike question that has echoed through human consciousness for millennia. When we look up at the stars, are any of them home to worlds like ours? For most of human history, this question lived purely in the realm of imagination. Ancient philosophers wondered about it, science fiction writers dreamed about it, and astronomers could only speculate. The stars were beautiful, distant points of light, but what they might harbour remained a mystery wrapped in the vast darkness of space. The challenge was both elegant and frustrating. Stars are incredibly bright, while planets are comparatively dim. Trying to spot a planet orbiting another star is a bit like trying to see a firefly buzzing around a lighthouse from hundreds of miles away while wearing sunglasses. The star's brilliant light drowns out any hope of directly observing the tiny, reflected glow of an orbiting world. But humans are remarkably clever when it comes to solving seemingly impossible puzzles. If we couldn't see these distant planets directly, perhaps we could detect them indirectly. Perhaps we could read the subtle signs they leave behind as they dance their ancient orbital choreography around their parent stars. This is where our story truly begins, not with a dramatic discovery or a eureka moment, but with patience, ingenuity, and the quiet determination of scientists who believed that if these worlds existed, there had to be a way to find them. Picture this. It's the early 1992nd. The internet is still a novelty. Mobile phones are the size of bricks, and most people couldn't imagine carrying a computer in their pocket. In astronomical terms, we knew of exactly 0 planets beyond our solar system. Not a single confirmed exoplanet existed in our catalogues. The universe, as far as we could prove, contained just one planetary system, ours. But that was about to change in the most unexpected way. The first confirmed exoplanet wasn't discovered orbiting a sun-like star in some distant, peaceful corner of the galaxy. Instead, it was found in one of the most violent environments imaginable around a pulsar, the rapidly spinning remnant of a massive star that had exploded in a supernova. These cosmic lighthouses spin hundreds of times per second, sending out beams of radiation like a celestial lighthouse gone mad. In 1992, astronomers Alexander Volshan and Dale Frail were studying a pulsar called PSRB 1257+12 when they noticed something peculiar. The incredibly precise timing of the pulsar's radio pulses, normally as regular as the universe's most accurate clock, showed tiny, rhythmic variations. Something was tugging at the pulsar, causing it to wobble ever so slightly in its rotation. That something turned out to be planets. Not one, but 3 worlds orbiting this stellar corpse in the constellation Virgo. These weren't worlds where life could flourish. The radiation from the pulsar would sterilize anything unfortunate enough to exist on their surfaces. But they were planets nonetheless, and their discovery shattered our cosmic loneliness in the most profound way. Suddenly, we knew we weren't alone in harboring worlds. The universe was populated with planets, even in the most unlikely places. If planets could survive the violent death of their parent star and continue orbiting a pulsar, then surely gentler, sun-like stars might host their own families of worlds. The hunt was on. Just 3 years later, in 1995, Swiss astronomers Michel Mayor and Didier Queloz made a discovery that would revolutionize our understanding of planetary systems. Using a telescope in the south of France, they detected the first exoplanet orbiting a main sequence star, a star similar to our Sun. The planet, which they called 51 Pegasi b, was nothing like anything in our solar system. It was roughly half the mass of Jupiter, but orbited its star in just 4 days, completing a full year faster than Earth completes a week. The temperatures on its surface would exceed 1,000 degrees Celsius, hot enough to melt copper. It was a world of extremes, a gas giant hugging its star so closely that it challenged everything astronomers thought they knew about how planetary systems form. This discovery opened the floodgates. Within a few years, dozens of exoplanets were being discovered. Within a decade, hundreds. Today, we know of over 5,000 confirmed exoplanets, with thousands more candidates waiting for confirmation. The lonely universe we once imagined has revealed itself to be teeming with worlds. But how exactly do we find these distant planets? How do we detect something so small and dim across such vast distances? The answer lies in some of the most elegant detective work in all of science. The primary method astronomers use is called the transit method, and it's beautifully simple in concept. Imagine you're sitting in a comfortable chair, watching a bright streetlight outside your window. Now picture a moth flying between you and that light. For just a moment, the moth blocks a tiny portion of the light, causing it to dim slightly. If the moth flies in a regular pattern, circling the light every few minutes, you could predict when the next dimming would occur, even if the moth itself was too small to see clearly. This is essentially what happens when a planet transits across the face of its star. From our perspective on Earth, the planet appears as a tiny dark dot moving across the brilliant stellar disk, blocking a minuscule fraction of the star's light. The star dims by perhaps 1% or less, a change so subtle that it requires incredibly precise instruments to detect. But when this dimming happens regularly every few days, weeks, or months, it tells us something extraordinary. There's a world out there, faithfully orbiting its star, crossing in front of it from our point of view with clockwork precision. The beauty of the transit method lies not just in its simplicity, but in what it can tell us about these distant worlds. The amount of light blocked reveals the planet's size. Larger planets block more light than smaller ones, the time it takes for the transit to occur, tells us about the planet's orbital speed and distance from its star. The period between transits reveals the length of the planet's year. More remarkably still, by studying the starlight that filters through a transiting planet's atmosphere, if it has one, we can begin to determine what gases are present in that alien sky. We can detect water vapor, carbon dioxide, methane, and other molecules that might hint at the conditions on these distant worlds. It's like cosmic archaeology, piecing together the story of an entire world from the faintest whispers of light that have travelled across the galaxy to reach our telescopes. Another method, called the radial-velocity or Doppler technique, relies on a different kind of stellar dance. Just as a planet orbits its star, the star also moves wobbling slightly in response to the gravitational tug of its planetary companion. This wobble causes the star to move alternately toward and away from Earth in its orbit, shifting the wavelength of its light in a phenomenon known as the Doppler effect. When the star moves toward us, its light is compressed to slightly bluer wavelengths. When it moves away, the light is stretched to redder wavelengths. By measuring these tiny shifts with extraordinary precision, astronomers can detect the presence of planets and determine their mass, orbital period, and distance from their star. These methods have revealed a universe far stranger and more diverse than we ever imagined. We've discovered planets that orbit two stars simultaneously, creating alien sunsets where twin suns hang in the sky. We found worlds made entirely of diamond, planets where it rains molten glass sideways, and others where the atmospheric pressure would crush a human instantly. There are planets so close to their stars that their surfaces are molten oceans of rock, and others so far away that they drift through the cosmic deep freeze of interstellar space. Some worlds are tidally locked, with one side permanently facing their star in eternal day, while the other side remains frozen in perpetual night. And then there are the planets that capture our imagination most intensely, those that might, just might, be something like home. These are the worlds that orbit within what astronomers call the habitable zone, or, more poetically, the Goldilocks zone, that orbital sweet spot where liquid water might exist on a planet's surface. Not too hot that water boils away into space, and not too cold that it freezes solid forever, but just right for the delicate chemistry of life as we know it. The search for these potentially habitable worlds has become one of the most compelling quests in modern astronomy. Each discovery brings us closer to answering that fundamental question that started our journey: are we alone? But finding planets in the habitable zone is just the beginning. A world might have liquid water and still be utterly hostile to life. It might lack a protective magnetic field, leaving its surface bathed in lethal radiation. Its atmosphere might be too thick or too thin, too poisonous or too reactive. The star it orbits might be prone to violent flares that periodically sterilize its planetary companions. Yet with each new discovery, we're learning that the universe is far more hospitable to worlds than we once believed. Planets are not rare cosmic accidents, but appear to be the natural, inevitable result of star formation. Nearly every star we've studied seems to host at least one planet, and many have entire families of worlds. This revelation has profound implications for our understanding of our place in the universe. If planets are common, and if some fraction of those planets exist in conditions suitable for liquid water, then the raw materials for life, at least life as we understand it, might be scattered throughout the galaxy. As we drift deeper into this cosmic story, we'll explore some of the most remarkable worlds we've discovered. From scorching hot Jupiters that orbit their stars in mere days to mysterious super-Earths that have no analogue in our solar system, we'll visit frozen worlds where subsurface oceans might harbour life, and desert planets where the very rocks might preserve signs of ancient biology. But perhaps most exciting of all, we'll discover how the next generation of space telescopes promises to revolutionize our search for alien worlds, potentially giving us our first glimpse of truly Earth-like planets, and maybe, just maybe, the first hints that we are not alone in this vast, star-filled cosmos. The universe, it turns out, is far stranger, more diverse, and more wonderful than we ever dared imagine, and we're only just beginning to explore it. As we float gently through this cosmic catalogue of worlds, let's pause to appreciate just how extraordinary this golden age of discovery truly is. In the span of a single human generation, we've gone from knowing nothing about planets beyond our solar system to having a vast library of alien worlds at our fingertips. It's as if we opened a door we didn't even know existed and found an entire universe waiting on the other side. The numbers alone are breathtaking. Every week, sometimes every day, new exoplanets are announced. Our catalogues now contain worlds orbiting red-dwarf stars that burn with the gentle glow of embers, massive blue giants that blaze with the fury of cosmic furnaces, and humble yellow stars much like our own sun. Some of these worlds are older than our entire solar system, ancient planets that formed when the universe was young and have been quietly orbiting their stars for billions upon billions of years. But it's not just the quantity of these discoveries that takes your breath away, it's their sheer diversity. The universe, as it turns out, is an incredibly creative architect when it comes to building planets. Every world we discover seems to push the boundaries of what we thought was possible, revealing new ways that gravity, chemistry, and time can collaborate to sculpt entire worlds. Take, for instance, the hot Jupiters, those massive gas giants we mentioned earlier, that huddle impossibly close to their parent stars. When 51 Pegasi b was first discovered, astronomers were baffled. How could a planet larger than Jupiter exist in an orbit that would take it inside the orbit of Mercury in our solar system? According to everything we understood about planetary formation, it should have been impossible. Gas giants, we believed, could only form far from their stars where it's cold enough for ice and gas to condense. Yet here was a world the size of Jupiter experiencing surface temperatures hot enough to vaporize metals, completing an orbit in just 4 days. The discovery forced us to completely reimagine how planetary systems evolve. We now know that many planets don't stay where they're born. They migrate, sometimes drifting slowly inward over millions of years due to gravitational interactions with the disk of gas and dust from which they formed. Some hot Jupiters may have started life as distant, cold worlds, before spiraling inward to their current scorching orbits. It's planetary wandering on a scale that would make ancient nomads weep with envy. These hot Jupiters are worlds of extremes that challenge our earthly intuitions about what a planet can be. On their day sides, where they face their star in permanent noon, temperatures soar to over 2,000 degrees Celsius. Metals don't just melt, they boil into vapor and rise into the atmosphere before condensing into metallic clouds. Some of these worlds likely experience weather systems where molten iron falls as rain. The night sides tell a different story entirely. Because many hot Jupiters are tidally locked with one face permanently pointed toward their star and the other trapped in eternal darkness, the temperature difference between day and night can be enormous. While the day side glows like a forge, the night side might be hundreds of degrees cooler, creating winds that race around the planet at thousands of kilometers per hour as the atmosphere tries to balance these temperature extremes. But if hot Jupiters represent one extreme of planetary possibility, then perhaps the most intriguing discoveries lie at the other end of the spectrum, the super-Earths and mini-Neptunes that seem to dominate planetary systems throughout the galaxy. Super-Earths are exactly what they sound like, rocky planets larger than Earth but smaller than Neptune. They're typically between 1.25 and 2 times the size of our homeworld, with masses that can be anywhere from slightly heavier than Earth to nearly 10 times more massive. What makes them particularly fascinating is that they represent a type of planet that simply doesn't exist in our solar system. In our cosmic neighborhood, there's a curious gap. We have small, rocky planets like Earth and Mars, and we have large gas giants like Jupiter and Neptune, but we have nothing in between. Yet when we look out into the galaxy, we find that super-Earths are among the most common types of planets. It's as if our solar system is missing an entire category of world that nature seems to prefer. These super-Earths could be many different things. Some might be rocky worlds with thicker atmospheres and stronger gravity than Earth, places where a human visitor would feel significantly heavier and where the air pressure might be crushing. Others could be water worlds, planets covered entirely by oceans that could be hundreds of kilometers deep, with no continents or dry land anywhere on their surface. Still, others might be something entirely alien worlds, with atmospheres so thick they create a runaway greenhouse effect, turning the surface into a hellish landscape of molten rock and crushing pressure. Or perhaps they're covered in exotic forms of ice, compressed by gravity into crystalline structures we've never seen on Earth. The mini-Neptunes present their own mysteries. These worlds are smaller than Neptune but larger than Earth, and they seem to occupy a sweet spot in planetary formation that makes them incredibly common. Many appear to have thick atmospheres of hydrogen and helium wrapped around rocky cores, creating worlds that might look like smaller, gentler versions of our ice giants. But here's what's particularly captivating about both super-Earths and mini-Neptunes. Some of them orbit within their star's habitable zone. These are worlds that might have the right temperature for liquid water to exist on their surfaces, if they have surfaces we can recognize. They represent our best current candidates for finding planets where life might have taken hold. Imagine standing on the surface of a super-Earth in the habitable zone. The horizon would curve more sharply than on Earth due to the planet's larger size. If you could jump, you wouldn't get as high due to the stronger gravity, but you might be able to see farther across the landscape. The sun in the sky might be a different color than our yellow sun, perhaps the orange glow of a red dwarf, or the brilliant white of a star, slightly more massive than our own. The day might be longer or shorter than Earth's 24-hour cycle. Some exoplanets complete a rotation in just a few hours, while others take weeks to turn once on their axis. The seasons, if they exist at all, might follow patterns completely foreign to our earthly experience. And then there are the truly exotic worlds that seem to exist purely to challenge our assumptions about what planets can be. There's HD 219134b, a super-Earth that orbits so close to its star that its year lasts just 3 days, and its surface temperature reaches 700 degrees Celsius. There's Kepler 78 billion reals, a planet almost exactly the size of Earth, but orbiting its star so closely that its surface is likely a molten ocean of rock. One of the most intriguing discoveries is WASP 12b, a hot Jupiter that's being slowly devoured by its star. The planet's atmosphere is being stripped away and consumed, creating a glowing tail of material that trails behind the world as it orbits. It's planetary cannibalism on a cosmic scale, a reminder that even worlds can have finite lifetimes. Perhaps even stranger is PSR J1719 to 1438b, a planet that appears to be made largely of crystallized carbon, essentially a diamond the size of Jupiter. This world orbits a pulsar so closely that it completes an orbit every 2 hours and 10 minutes. The intense gravitational forces and radiation have compressed what was once likely a white dwarf star into what might be the most valuable object in the known universe, if anyone could figure out how to mine a diamond planet. Then there are the rogue planets, worlds that have been ejected from their star systems entirely and now drift alone through the cold depths of interstellar space. These orphan worlds experience no sunrise or sunset, no seasons, no warmth from any nearby star. They're planets in permanent winter, illuminated only by the faint glow of distant stars, and perhaps the heat from their own slowly cooling cores. Yet even these lonely wanderers capture our imagination. Some might retain enough internal heat to maintain subsurface oceans beneath thick shells of ice. In the eternal darkness between the stars, life might still find a way, sustained not by sunlight, but by the planet's own geological energy. The diversity of exoplanets has also revealed something profound about planetary formation itself. We're learning that the process of building worlds is far messier, more chaotic, and more creative than we ever imagined. Planets migrate, collide, merge, and get ejected from their systems. They can switch orbits, change their atmospheric composition over time, and even capture moons from other worlds. This dynamic view of planetary evolution has important implications for understanding habitability. A world that starts life as a frozen ice ball might migrate closer to its star and become a temperate, potentially habitable world. Conversely, a planet that begins in the habitable zone might drift outward over time, freezing into a barren ice world. The story of planetary formation is still being written with each new discovery. We're finding planets forming around very young stars, worlds that are still hot from their recent birth. We're discovering planets around ancient stars that have been shining since the universe was less than 1 billion years old. Each discovery adds another piece to the puzzle of how planets form, evolve, and potentially develop the conditions necessary for life. But perhaps the most exciting aspect of exoplanet research isn't just the worlds we've already found, it's the promise of what we might discover next. The field is advancing so rapidly that textbooks become outdated almost as soon as they're published. New techniques for detecting and studying exoplanets are being developed constantly, each one opening new windows into the nature of these distant worlds. Direct imaging, actually taking pictures of exoplanets rather than detecting them indirectly, is beginning to yield its first results. These images show not detailed surface features, but simple points of light that represent entire alien worlds. Yet even these humble dots of light contain a wealth of information about planetary atmospheres, temperatures, and orbital characteristics. Future space telescopes promise to revolutionize our understanding even further. These observatories will be capable of detecting smaller, more Earth-like planets and analyzing their atmospheres in unprecedented detail. They might even be able to detect seasonal changes on distant worlds, watching as alien weather patterns shift and evolve over months and years. The ultimate goal, of course, is to find signs of life itself. This might come in the form of atmospheric biosignatures, combinations of gases that would be difficult to explain without biological processes. On Earth, the presence of both oxygen and water vapor in our atmosphere is a strong indicator of life, since oxygen is highly reactive and would disappear quickly without something continuously replenishing it. Finding similar biosignatures around other stars would represent one of the most profound discoveries in human history. It would tell us that life is not unique to Earth, that the universe might be filled with living worlds, each one conducting its own biological experiments in the laboratory of cosmic evolution. As we drift through these contemplations of alien worlds and distant possibilities, it's worth pausing to appreciate the profound shift in perspective that exoplanet discoveries have brought to humanity. Just a few decades ago, we could only wonder whether planets existed around other stars. Today, we know they're everywhere. This knowledge has transformed our understanding of our place in the cosmos. We're no longer inhabitants of the only known planetary system, but citizens of a galaxy that appears to be teeming with worlds. Some of these worlds might harbour life, others might be stepping stones to future human exploration, and still others might teach us new physics or chemistry that we never could have learned from studying our solar system alone. The search for exoplanets represents one of the most successful detective stories in the history of science. Armed with nothing more than the subtle variations in starlight and the patient application of physical laws, we've discovered thousands of worlds across hundreds of light years of space. We've learned to read the whispers that these distant planets write in the language of gravity and light. And we're still in the early chapters of this story. Each new world we discover adds to our understanding of how planets form, evolve, and potentially develop the conditions for life. Each new technique we develop for studying these distant worlds brings us closer to answering the fundamental questions that have driven this entire quest. Are we alone in the universe? Are there other worlds where life has taken hold? Might there be civilizations on distant planets, looking back at our sun and wondering the same things we wonder about them? These questions, which once belonged purely to the realm of philosophy and speculation, are now being addressed through rigorous scientific investigation. We may be on the verge of discoveries that will reshape our understanding of life, intelligence, and our cosmic significance. But even if we never find definitive signs of life around other stars, the search itself has already transformed us. It has expanded our vision of what's possible, shown us the incredible creativity of cosmic evolution, and reminded us that we live in a universe far stranger and more wonderful than we ever dared imagine. As you settle deeper into your evening rest, let these thoughts of distant worlds drift through your consciousness like gentle waves. Somewhere out there, alien sunsets are painting foreign skies with colours we've never seen. Strange weather patterns are sculpting landscapes we can barely imagine. And perhaps, just perhaps, other forms of life are looking up at their own night sky, wondering about the worlds that might orbit other stars. The universe is vast, mysterious, and filled with more planets than there are grains of sand on all the beaches of Earth, and we're just beginning to explore it. The story of exoplanet discovery isn't just about the worlds themselves, it's about the remarkable ingenuity humans have shown in learning to listen to the universe's subtlest whispers. When you consider the technical challenges involved, it's almost miraculous that we've managed to detect these distant worlds at all. Think about the scales we're dealing with. The nearest star to our Sun is over 4 light-years away, that's roughly 25 trillion miles. At those distances, even the largest planets appear as nothing more than mathematical abstractions hidden in the noise of stellar brightness. It's like trying to spot a moth flying around a lighthouse from the next city over, while wearing a blindfold during a thunderstorm. Yet astronomers have developed techniques so precise, so sensitive, that they can measure changes in starlight, equivalent to detecting the dimming caused by a fruit fly crossing in front of a car headlight from hundreds of miles away. The instruments required for this cosmic detective work push the boundaries of what's technologically possible. Take the Kepler Space Telescope, launched in 2009 and responsible for discovering thousands of exoplanets. This remarkable observatory stared unblinkingly at a single patch of sky, containing about 150,000 stars, monitoring their brightness with unprecedented precision. It could detect changes in stellar brightness of just a few parts per million variations, so tiny that they would be completely overwhelmed by the turbulence of Earth's atmosphere. Kepler's method was elegantly simple in concept, but fiendishly difficult in execution. By watching for the periodic dimming that occurs when a planet transits across its star's face, the telescope could identify not just the presence of planets, but determine their size, orbital period, and distance from their host star. Over its primary mission and extended operations, Kepler discovered over 2,600 confirmed exoplanets and identified thousands more candidates. But Kepler's story also illustrates the challenges of exoplanet hunting. The spacecraft had to maintain incredibly precise pointing accuracy to keep its gaze steady on the same stars for months and years at a time. When mechanical failures eventually ended its primary mission, astronomers had to develop creative new observation strategies to continue the search for distant worlds. The successor mission, TESS, the Transiting Exoplanet Survey satellite, has taken a different approach, surveying the entire sky in segments, looking for transiting planets around the brightest nearby stars. This strategy trades depth for breadth, potentially discovering planets around stars close enough for detailed follow-up studies with future telescopes. Ground-based observatories have also revolutionized exoplanet detection through the radial-velocity method. These instruments measure the Doppler shift in starlight caused by a star's gravitational wobble as planets orbit around it. The precision required is extraordinary. Astronomers need to detect velocity changes as small as 1 meter per second, roughly the speed of a leisurely walk. To put this in perspective, imagine trying to measure whether someone walking on the other side of the city is speeding up or slowing down by a single step, and doing so by analyzing the sound of their footsteps carried on the wind. That's essentially what radial velocity measurements accomplish, but with starlight instead of sound. These techniques have revealed that planetary systems come in a bewildering variety of configurations. Some stars host single planets in lonely orbits. Others have multiple worlds packed so tightly together that their years last just days or weeks. There are systems where planets orbit in perfect resonance, completing 2 or 3 orbits for every orbit of their neighbours, creating a cosmic clockwork of gravitational harmony. Then there are the systems that challenge our understanding of orbital dynamics entirely. Kepler 36, for instance, hosts 2 planets that orbit so close to each other that they periodically come within just 5 planetary radii of collision. When the larger planet appears in the sky of its smaller companion, it would loom 30 times larger than our moon appears from Earth, a sight that would dominate the alien heavens. Some planetary systems are tilted at impossible angles. While the planets in our solar system orbit roughly in the same plane as the Sun's equator, many exoplanet systems show wild orbital inclinations. Some planets orbit backwards compared to their star's rotation, while others follow highly elliptical paths that carry them from scorching proximity to frigid distance over the course of each orbit. These orbital oddities tell stories of violence and chaos in planetary system formation. Planets can be scattered into bizarre orbits by gravitational encounters with other worlds, by close passes with neighbouring stars, or by the complex dynamics of forming in a disk of gas and debris around a young star. What we once thought of as the orderly, predictable clockwork of our solar system turns out to be just one possible outcome among many. Perhaps most intriguingly, we've discovered that many stars host planets in configurations that would be completely unstable in our solar system. There are worlds that orbit so close to their stars that they complete multiple orbits in a single Earth day. Others follow such elliptical paths that they experience wild temperature swings, from furnace heat to Arctic cold, over the course of each year. The atmospheres of these exoplanets represent another frontier of discovery. When a planet transits across its star, a tiny fraction of starlight passes through the planet's atmosphere before reaching Earth. By analysing this filtered light with incredible precision, astronomers can determine what gases are present in alien skies. We've detected water vapour in the atmospheres of distant worlds, along with carbon monoxide, methane, and even exotic compounds that don't exist naturally on Earth. Some planets have atmospheres so dense that the surface pressure would be crushing, while others have atmospheres so thin they're barely detectable. There are worlds where the atmospheric chemistry changes dramatically between day and night sides, and others where global winds redistribute heat and matter in patterns we're only beginning to understand. One of the most remarkable atmospheric discoveries came from studying HD 209458b, a hot Jupiter located about 150 light-years from Earth. This planet not only transits its star regularly, making it ideal for atmospheric studies, but it's also gradually losing its atmosphere to space. The intense radiation from its nearby star is heating the planet's upper atmosphere so much that hydrogen is escaping into space, forming a comet-like tail of gas that streams behind the planet as it orbits. This process, called atmospheric escape, might be common among planets that orbit very close to their stars. Over millions or billions of years, some worlds might lose their entire atmospheres, transforming from gas-rich mini-Neptunes into bare, rocky super-Earths. It's planetary evolution in action, observable across cosmic time. The search for potentially habitable worlds has become increasingly sophisticated as our detection methods improve. The habitable zone, that orbital region where liquid water might exist on a planet's surface, is no longer viewed as a simple ring around each star. Instead, we now understand that habitability depends on a complex interplay of factors, including atmospheric composition, greenhouse effects, magnetic fields, and stellar activity. A planet might orbit within the traditional habitable zone, but still be hostile to life as we know it. If it lacks a substantial atmosphere, any surface water would boil away into space. If its atmosphere is too thick, a runaway greenhouse effect might turn the surface into a hellish furnace. If the planet lacks a magnetic field, stellar radiation could strip away both atmosphere and any surface water over geological time. Conversely, worlds that orbit outside the conventional habitable zone might still harbour conditions suitable for life. Planets with thick atmospheres and strong greenhouse effects might maintain liquid water on their surfaces even at distances where they would otherwise be frozen. Tidal heating from gravitational interactions with other planets or their star might keep subsurface oceans liquid even on worlds far from their star. The moons of exoplanets, exomoons, represent another exciting frontier, though they remain tantalizingly difficult to detect with current technology. In our solar system, moons like Europa and Enceladus harbour subsurface oceans that might be more hospitable to life than any environment on their parent planets. If similar moons exist around exoplanets, they could dramatically expand the number of potentially habitable worlds in the galaxy. Consider the possibilities. A large moon orbiting a gas giant in the habitable zone might have stable temperatures, a substantial atmosphere, and surface oceans. Unlike planets that are tidally locked to their stars, such a moon would experience regular day-night cycles as it orbits its parent planet. The gravitational interactions between moon and planet might drive geological activity that could help regulate climate and atmospheric composition over long time periods. Some of the most exciting exoplanet discoveries have come from studying multiple planet systems, where we can observe how different worlds form and evolve in the same stellar environment. The TRAPPIST-1 system, located just 40 light-years from Earth, contains 7 Earth-sized planets, packed into orbits smaller than Mercury's around our Sun. 3 of these worlds orbit within their star's habitable zone, making this system one of the most promising targets for detailed atmospheric studies. What makes TRAPPIST-1 particularly fascinating is that all 7 planets appear to be in resonant chains. Their orbital periods are related by simple mathematical ratios. This suggests that the planets formed farther out in their system and migrated inward together, maintaining their gravitational relationships as they moved. It's a cosmic ballet of world formation that we can study in remarkable detail. The star at the center of the TRAPPIST-1 system is an ultra-cool dwarf, much smaller, cooler, and longer-lived than our Sun. These types of stars are the most common in our galaxy, and their longevity means that planets orbiting them have had billions of years to develop and maintain stable conditions. If life exists around such stars, it might be far more common than life around Sun-like stars simply because there are so many more opportunities for it to arise and persist. Ultra-cool dwarfs present their own challenges for habitability, however. Planets in their habitable zones must orbit very close to receive enough energy for liquid water, which often means they become tidally locked with permanent day and night sides. The stellar radiation might also be problematic, as these small stars can produce powerful flares that could strip away planetary atmospheres or sterilize any life on the surface. Yet recent research suggests that tidally locked planets might be more habitable than previously thought. Atmospheric circulation could transport heat from the day side to the night side, moderating temperatures across the planet. The permanent twilight zone between day and night might offer particularly stable conditions for life to develop and thrive. As we continue to discover and study exoplanets, we're building a statistical understanding of how common different types of worlds are throughout the galaxy. Current estimates suggest that virtually every star hosts at least one planet, and many have multiple worlds. Small, rocky planets appear to be extremely common, while large gas giants are less frequent but still numerous. Perhaps most remarkably, we're learning that planetary systems like our own, with small, rocky planets close to the star and large gas giants farther out, might be relatively uncommon. Most planetary systems discovered so far have configurations quite different from ours, with super-Earths and hot Jupiters being far more typical than anything in our solar system. This raises profound questions about how typical or unusual Earth might be. Are we inhabitants of a rare type of planetary system that happens to be particularly conducive to life? Or are there many different pathways to habitability, most of which look nothing like the conditions that gave rise to life on our world? The next generation of telescopes and instruments promises to address these questions with unprecedented detail and precision. The James Webb Space Telescope, already revolutionizing our understanding of exoplanet atmospheres, can analyze the chemical composition of alien skies with extraordinary sensitivity. Future space telescopes designed specifically for exoplanet research will be capable of directly imaging Earth-like worlds around nearby stars and searching their atmospheres for signs of biological activity. The possibility of detecting biosignatures, chemical indicators of life in exoplanet atmospheres, represents one of the most exciting frontiers in modern astronomy. On Earth, the combination of oxygen and water vapor in our atmosphere would be difficult to explain without photosynthetic life continuously replenishing the oxygen. Similar combinations of gases around other worlds might provide the first definitive evidence that life exists elsewhere in the universe. But biosignature detection comes with significant challenges. We need to understand how non-biological processes might produce similar chemical signatures, and we need instruments sensitive enough to detect trace gases in the thin atmospheres of distant worlds. The search for life will require not just technological advances, but also a deeper understanding of how life might manifest itself in environments very different from Earth. As you drift towards sleep tonight, let these thoughts of distant worlds and future discoveries wash over you like gentle waves. Somewhere in the galaxy, alien sunsets are painting skies we can barely imagine. Strange weather systems are shaping landscapes that have never known human footsteps. And perhaps, in ways we haven't yet learned to recognize, life itself is stirring in environments so different from our own that they challenge our very definition of what it means to be alive. The universe has revealed itself to be far more creative and diverse than we ever dared hope. Each new world we discover adds another verse to the cosmic poem of planetary formation and evolution. And we've only just begun to read the opening stanzas of this epic tale. The search for worlds that might harbour life has led us to some of the most remarkable discoveries in the history of astronomy. But perhaps what's most astounding isn't just the sheer number of potentially habitable planets we've found, it's how they've challenged our assumptions about what habitable even means. For decades, our concept of habitability was deeply Earth-centric. We imagined that life required conditions very much like those on our own world, a rocky planet orbiting at just the right distance from a sun-like star, with liquid water on its surface, and an atmosphere not too different from our own. It was a cosmic case of looking for our car keys under the streetlight, not because that's where we lost them, but because that's where we could see. But the universe, as we're learning, is far more imaginative than our limited Earth-based perspective allowed. The exoplanets we've discovered have expanded our definition of habitability in ways that would have seemed like science fiction just a generation ago. Consider Proxima Centauri b, the closest known exoplanet to Earth, at just over 4 light-years away. This world orbits within the habitable zone of Proxima Centauri, a red-dwarf star that's much smaller and cooler than our Sun. But Proxima Centauri b likely receives intense stellar radiation from its host star, which is known for producing powerful flares that could strip away atmospheric gases over time. Yet recent studies suggest this planet might still be habitable under certain conditions. If it has a substantial atmosphere, perhaps one dominated by carbon dioxide like Venus, greenhouse warming might allow liquid water to exist despite the hostile radiation environment. The planet might even have a magnetic field strong enough to deflect some of the stellar wind and radiation. More intriguingly, if Proxima Centauri b is tidally locked with one side permanently facing its star, The border region between eternal day and eternal night might offer surprisingly clement conditions. This twilight zone could maintain temperatures suitable for liquid water, while being partially shielded from the worst of the stellar radiation. It's a reminder that habitability might exist in configurations we never considered when we only had one example, our own world, to guide our thinking. The concept of tidally locked planets has opened up entirely new categories of potentially habitable environments. On Earth, we're accustomed to the regular cycle of day and night, the changing of seasons, the dynamic weather patterns driven by our planet's rotation and axial tilt. But a tidally locked world presents a radically different scenario. Picture standing on the day side of such a planet. The sun would hang motionless in the sky, never rising or setting, casting eternal shadows that never shift or change. The landscape would be bathed in permanent noon, with temperatures that might soar far above the boiling point of water. It would be a realm of extremes, scorching deserts, perhaps even oceans of molten rock under the relentless stellar glare. Walk toward the night side, however, and you'd enter a realm of perpetual darkness and bitter cold. Here, any atmosphere would condense and freeze, creating a landscape of exotic ices under a sky filled with distant stars but never touched by the warmth of the nearby sun. But between these extremes lies the terminator, the boundary between day and night that circles the planet like a permanent sunset strip. Here, the temperature might be just right for liquid water, and the atmospheric dynamics could create weather patterns unlike anything on Earth. Winds might flow constantly from the hot day side to the cold night side, creating rivers of air that could moderate temperatures and distribute heat across the planet's surface. Recent climate models suggest that such worlds might be far more habitable than we initially thought. The atmosphere itself becomes a heat redistribution system, carrying warmth from the day side to the night side and creating temperate zones where life might flourish. It's a type of climate that has no analogue on Earth, but might be incredibly common throughout the galaxy. Then there are the super-Earths that have captured so much scientific attention. These worlds, larger than Earth but smaller than Neptune, might represent the most common type of potentially habitable planet in the universe, yet we have no direct experience with what such worlds might be like. A super-Earth with twice the mass of our planet would have significantly stronger surface gravity. If you could somehow visit such a world, you'd weigh twice as much as you do on Earth. Walking would be more difficult, jumping would be impossible, and the very structure of any life forms that evolved there might be radically different from terrestrial biology. But stronger gravity might also create advantages for habitability. A more massive planet could retain its atmosphere more easily over geological time, preventing the gradual loss of water and other volatile compounds to space. It might also drive more vigorous geological activity, with stronger plate tectonics that could help regulate global climate through the carbon cycle. The atmospheres of super-Earths could be dramatically different from Earth's thin envelope of air. Some might have atmospheres so thick that they create crushing surface pressures, while others might maintain temperate conditions under a blanket of dense, warm air. The weather patterns on such worlds could be driven by atmospheric dynamics. We can barely imagine perhaps global wind systems that dwarf anything we see on Earth, or storm systems that persist for centuries. Water worlds represent another fascinating possibility for habitability. These are planets that might be covered entirely by oceans, with no continents or dry land anywhere on their surface. Such worlds could have water layers hundreds or even thousands of kilometers deep, creating pressures at the bottom that would compress water into exotic forms of ice despite the crushing heat. The biology of such worlds would necessarily be entirely aquatic, but that doesn't make them less hospitable to life. Earth's oceans teem with biodiversity, and much of the early evolution of life on our planet took place entirely in marine environments. A water world might support complex ecosystems, from its sunlit surface layers down to the mysterious depths where strange chemistries might flourish in the eternal darkness. Some water worlds might have subsurface oceans beneath thick shells of ice, similar to Jupiter's moon Europa or Saturn's moon Enceladus. These hidden seas could be kept liquid by tidal heating from their host star or by the gravitational pull of other planets in their system. Such worlds might appear lifeless from the outside while harboring thriving ecosystems in the dark waters below. The discovery of potentially habitable exomoons has added yet another dimension to our search for life. Large moons orbiting gas giant planets in their star's habitable zone might offer some of the most stable and long-lived habitable environments in the galaxy. Unlike planets that might be tidally locked to their stars, such moons would experience regular day-night cycles as they orbit their parent planet. The gravitational interactions between a large moon and its parent planet could drive geological activity that helps maintain a stable climate over billions of years. Volcanic activity could recycle atmospheric gases, while tidal forces might keep subsurface oceans liquid even in conditions that would otherwise be too cold for life. Imagine standing on such a moon and watching its parent planet rise and set in the sky like an enormous, ever-changing celestial companion. The planet might appear dozens of times larger than our moon appears from Earth, dominating the sky with its swirling clouds and dynamic weather systems. The gravitational dance between moon and planet might create spectacular tidal effects, perhaps driving geysers that shoot water and organic compounds high into the thin atmosphere. As we've expanded our understanding of where life might exist, we've also had to reconsider what types of stars might host habitable worlds. Red-dwarf stars, which are much smaller and cooler than our Sun, make up about 3/4 of all stars in the galaxy. They also have incredibly long lifespans. Some will continue burning for trillions of years, far longer than the current age of the universe. This longevity has profound implications for habitability. While our Sun will eventually expand into a red giant and sterilize Earth in about 5 billion years, planets around red-dwarf stars might remain habitable for timescales that dwarf the entire history of complex life on our world. If life exists around such stars, it might have had vastly more time to evolve and develop than life on Earth. But red-dwarf stars also present unique challenges. Many are prone to powerful stellar flares that could strip away planetary atmospheres or sterilize surface life with intense radiation. The habitable zones around these stars are much closer in than Earth's orbit around the Sun, which often means that habitable planets become tidally locked. Yet recent research suggests that planets around red-dwarf stars might be more resilient than we initially thought. Strong magnetic fields could protect them from stellar radiation, while thick atmospheres might help redistribute heat and maintain temperate conditions even on tidally locked worlds. Perhaps most remarkably, we're beginning to find potentially habitable planets around some of the most ancient stars in the galaxy stars that formed when the universe was less than 1 billion years old. These ancient worlds have had an almost unimaginable amount of time for life to arise, evolve, and perhaps develop into forms of complexity that we can barely conceive. The statistical analysis of exoplanet discoveries has revealed patterns that have surprised even the astronomers making the discoveries. Small, rocky planets appear to be incredibly common, with recent estimates suggesting that virtually every star in the galaxy hosts at least one world smaller than Neptune. Many of these planets orbit within or near their star's habitable zone. If even a small fraction of these worlds actually harbor conditions suitable for life, the galaxy could contain billions of potentially habitable planets. The sheer scale of this possibility is breathtaking. We might be living in a universe where life is not rare and precious, but abundant and diverse beyond our wildest imagination. Yet, for all our discoveries, we're still searching for that one definitive sign that life exists beyond Earth. The detection of biosignatures in exoplanet atmospheres remains one of the holy grails of modern astronomy, a discovery that would rank among the most profound in human history. The James Webb Space Telescope has already begun analyzing the atmospheres of exoplanets with unprecedented detail, revealing the chemical composition of alien skies light years away. We've detected water vapor, carbon dioxide, and other familiar molecules, but also exotic compounds that don't exist in Earth's atmosphere. Future telescopes will push these capabilities even further, potentially allowing us to detect the subtle chemical signatures that might indicate biological processes. On Earth, the presence of oxygen and water vapor together in our atmosphere would be difficult to explain without photosynthetic life, continuously replenishing the oxygen. Similar biosignatures around other stars might provide our first concrete evidence that we are not alone. But we're also learning that the search for life requires us to think beyond Earth-based biology. Life on other worlds might use completely different chemistries, might thrive in environments that would be instantly lethal to terrestrial organisms, or might leave signatures in planetary atmospheres that we haven't yet learned to recognize. The possibility of detecting technosignatures, evidence of technological civilizations, adds another layer of excitement to exoplanet research. Advanced civilizations might alter their planet's atmosphere through industrial processes, or they might create artificial structures large enough to be detected from interstellar distances. While such discoveries would be extraordinarily unlikely, they're not impossible, and the search for them pushes our detection capabilities to their absolute limits. As we've learned more about exoplanets, we've also gained new perspective on our own world and solar system. Earth, once thought to be a typical rocky planet, now appears to be somewhat unusual in several important ways. Our large moon, which helps stabilize Earth's axial tilt and creates regular tides, might be rare among planetary systems. Our solar system's architecture, with small rocky planets close to the Sun and large gas giants farther out, doesn't match the most common exoplanet configurations we've discovered. Yet this doesn't make Earth uniquely special, it simply means that there are many different pathways to creating habitable worlds, most of which look nothing like our familiar solar system. The universe appears to be extraordinarily creative when it comes to building planets and planetary systems, and habitability might emerge in configurations we're only beginning to understand. The study of exoplanets has also revealed the dynamic nature of planetary evolution. Worlds don't simply form and remain static, they migrate, collide, lose their atmospheres, gain new ones, and undergo dramatic changes over geological time. A planet that starts its life as a frozen ice ball might migrate inward and become a temperate, potentially habitable world. Conversely, a world that begins in the habitable zone might be stripped of its atmosphere by stellar activity or gravitational interactions with other planets. This dynamic view of planetary evolution suggests that habitability itself might be a temporary condition for many worlds. The window of time during which a planet maintains conditions suitable for life might be brief in cosmic terms, or it might persist for billions of years depending on the specific circumstances of each world. The search for exoplanets has become one of the most rapidly advancing fields in all of astronomy. New worlds are being discovered regularly, and each discovery adds to our understanding of how planets form, evolve, and potentially develop the conditions necessary for life. The techniques for detecting and studying these distant worlds are becoming more sophisticated with each passing year. Direct imaging of exoplanets, actually taking pictures of these distant worlds rather than detecting them indirectly, is beginning to yield remarkable results. These images show not detailed surface features, but simple points of light that represent entire alien worlds. Yet even these humble dots of light contain a wealth of information about planetary temperatures, atmospheric composition, and orbital characteristics. The next generation of telescopes will revolutionize our ability to study exoplanets in detail. Future space observatories will be capable of directly imaging Earth-sized planets around nearby stars and analyzing their atmospheres for signs of water vapor, oxygen, and other gases that might indicate habitability or even biological activity. Ground-based telescopes are also becoming more powerful and precise. The new generation of extremely large telescopes, with mirrors 30 meters across or larger, will be able to study exoplanet atmospheres with unprecedented detail and might even be capable of detecting seasonal changes on distant worlds. As you settle into the quiet comfort of evening, let these thoughts of distant worlds and cosmic possibilities drift through your consciousness like gentle starlight. Somewhere in the galaxy, on worlds we're only beginning to discover, alien sunsets might be painting foreign skies with colors that have no names in any human language. Strange weather systems might be sculpting landscapes that have never known the touch of familiar rain or snow. Tides driven by alien moons might be washing shores of continents that exist only in our growing catalogues of distant worlds. And perhaps, in ways we haven't yet learned to recognize or understand, life itself might be stirring in environments so different from our own that they challenge our very conception of what it means to be alive. The universe has already shown us that it's far more creative and diverse than we ever dared hope. We stand at the threshold of discoveries that might reshape our understanding of life, intelligence, and our place in the cosmic story. The search for exoplanets has revealed a universe teeming with worlds, each one a unique experiment in the physics and chemistry of planetary formation. From scorching hot Jupiters that orbit their stars in mere days, to frozen rogue planets drifting alone in the darkness between stars, from super-Earths with crushing gravity to delicate water worlds covered by endless oceans, the gallery of exoplanets grows more diverse and more wonderful with each new discovery. And we've only just begun to explore this vast cosmic archive of worlds. Each new planet we detect brings us closer to answering the profound questions that have driven this entire quest. Are we alone? How common is life in the universe? Might there be other civilizations looking back at our sun and wondering the same things we wonder about them? These questions, which once lived purely in the realm of philosophy and speculation, are now being addressed through patient observation and rigorous scientific analysis. We may be just years or decades away from discoveries that will fundamentally change how we see ourselves and our place in the cosmic community. The exoplanets we've discovered remind us that we live in a universe far stranger, more beautiful, and more full of possibilities than we ever imagined. And somewhere out there, among the thousands of worlds we've already found, and the countless others yet to be discovered, there might just be another pale blue dot circling another ordinary star, harboring its own extraordinary story of life, evolution, and perhaps even intelligence. The search continues, patient and methodical, driven by the simple but profound desire to know whether we share this vast cosmos with others. And with each new world we discover, with each new technique we develop for studying these distant planets, we move a little closer to finding out. The question of whether we're alone in this vast cosmos has taken on new urgency as we've discovered just how abundant planets truly are. But finding worlds that could harbour life is only the first step in a much larger mystery. The real challenge lies in understanding what we're actually looking for when we search for signs of life itself. When astrobiologists, scientists who study the possibility of life beyond Earth first began thinking seriously about biosignatures, they naturally started with what they knew best: life on our own planet. Earth's atmosphere contains a mixture of gases that would be almost impossible to maintain without living organisms constantly replenishing them. Oxygen, for instance, is highly reactive and would disappear from our atmosphere within a few million years if plants and other photosynthetic organisms weren't continuously producing it. The combination of oxygen and water vapor in Earth's atmosphere creates what scientists call a disequilibrium, a chemical imbalance that can only be maintained by active biological processes. It's like finding a bathtub that's simultaneously draining and remaining full. There must be something actively filling it to maintain that impossible state. But as our understanding of exoplanets has grown more sophisticated, so too has our appreciation for how different alien life might be from the terrestrial variety we're familiar with. Life on Earth represents just one possible solution to the challenge of extracting energy from the environment and using it to grow, reproduce, and evolve. there might be entirely different approaches that we haven't yet learned to recognize. Consider the remarkable diversity of life in Earth's most extreme environments. In the crushing depths of the ocean, around hydrothermal vents where superheated water rich in minerals erupts from the seafloor, entire ecosystems thrive in conditions that would instantly kill most surface life. These creatures don't depend on sunlight for energy instead. They harness the chemical energy released by reactions between hot water and rock. In the acidic hot springs of Yellowstone, microorganisms flourish in water so corrosive it would dissolve human skin in minutes. In the high radiation environment around nuclear reactors, bacteria have evolved that actually feed on radiation itself, breaking down radioactive materials and using the energy for their metabolism. Deep beneath the Earth's surface, in rock formations miles underground, scientists have discovered microbial communities that have been isolated from the surface world for millions of years. These organisms survive on the tiny amounts of energy released by radioactive decay in the rocks around them, living their entire lives in perpetual darkness, at temperatures that would cook most surface life. If life on Earth can adapt to such extreme conditions, imagine what might be possible on worlds with completely different environmental conditions. On a planet orbiting close to a red-dwarf star, life might evolve to harness the constant bombardment of stellar radiation, turning what we consider a hostile environment into a source of energy. On a world with a thick atmosphere of carbon dioxide, organisms might develop entirely different approaches to photosynthesis, using wavelengths of light that would be useless to Earth plants. The search for biosignatures has led scientists to think creatively about what signs of life might look like on worlds very different from our own. On a planet with a methane-rich atmosphere, for instance, life might produce oxygen as a waste product, creating the same chemical disequilibrium we see on Earth, but through completely different biological processes. Some researchers have even proposed looking for industrial pollutants in exoplanet atmospheres, artificial compounds that could only be produced by technological civilizations. On Earth, our industrial activities have altered the composition of our atmosphere in ways that would be detectable from space. Chlorofluorocarbons, nitrogen oxides from agriculture, and even the heat signatures of our cities might be observable from interstellar distances with sufficiently advanced instruments. The James Webb Space Telescope has already begun this detective work in earnest. Its incredibly sensitive instruments can analyze starlight that has passed through exoplanet atmospheres during transits, breaking that light down into its component wavelengths to reveal the chemical fingerprints of different gases. It's like cosmic spectroscopy reading the recipe of an alien world's atmosphere from 40 light-years away. Early results from Webb have been both exciting and humbling. The telescope has detected water vapor, carbon dioxide, clouds, and even weather patterns on distant worlds. But it has also revealed just how complex and varied exoplanet atmospheres can be. Some worlds have atmospheric compositions unlike anything in our solar system, with exotic chemistries that challenge our understanding of how planetary atmospheres evolve. One particularly intriguing discovery came from studying the atmosphere of K2 to 18b, a sub-Neptune exoplanet about 120 light-years away. This world, which is more than twice the size of Earth, appears to have water vapor in its atmosphere and might even have clouds of liquid water droplets. But it's much larger than Earth and orbits a red-dwarf star, creating conditions that have no analogue in our solar system. The question of whether such a world could actually be habitable remains open. Its larger size means stronger gravity, which could affect atmospheric dynamics in ways we don't fully understand. The red dwarf star it orbits might subject the planet to intense stellar flares that could strip away its atmosphere over time. Yet the detection of water vapor suggests that at least some of the basic ingredients for life, as we know it, might be present. Perhaps even more tantalizing are the worlds where we've detected gases that are difficult to explain through purely geological processes. Phosphine, for instance, is a compound that on Earth is produced primarily by living organisms in oxygen-free environments. When astronomers reported detecting phosphine in the atmosphere of Venus, Though this detection remains controversial, it sparked intense debate about whether some form of microbial life might exist in the planet's upper atmosphere, where temperatures and pressures are more moderate than on the hellish surface below. The search for biosignatures has also led to some surprising insights about our own planet. When astronomers turn their most sensitive instruments toward Earth and analyze our atmosphere as if it were an exoplanet, they've discovered that some of our most distinctive biosignatures would be surprisingly difficult to detect from interstellar distances. The oxygen in Earth's atmosphere, for instance, is most easily detected in combination with water vapor. The presence of both gases together creates a stronger signal than either would produce alone. But this combination would only be detectable around relatively nearby stars with current technology. For more distant worlds, we might need to look for other signs of life that produce stronger atmospheric signals. This has led some researchers to propose looking for what they call biosignature gases compounds that life might produce in large quantities, and that would be easier to detect than oxygen. Dimethyl sulfide, for instance, is produced by marine algae on Earth and creates a distinctive spectral signature. Methyl chloride is produced by both plants and microorganisms and might accumulate in the atmospheres of worlds with different atmospheric chemistry than Earth's 2p. The challenge is distinguishing between gases produced by life and those created by non-biological processes. Methane, for example, can be produced by living organisms, but it can also be created by geological processes like volcanism or by chemical reactions in a planet's atmosphere. To confirm that methane in an exoplanet's atmosphere is actually a sign of life, astronomers would need to rule out these non-biological explanations. This detective work requires not just detecting the presence of different gases, but understanding the overall atmospheric chemistry of distant worlds. A planet with methane and oxygen in its atmosphere might be a strong candidate for hosting life, since these two gases react with each other and would quickly disappear unless something was continuously replenishing them. But a world with methane and carbon dioxide might simply be geologically active, with the methane produced by volcanic processes rather than biological ones. The search for life has also expanded beyond looking for individual gases to examining the overall behavior of exoplanet atmospheres. On Earth, seasonal changes in atmospheric composition reflect the annual cycle of plant growth and dormancy. During spring and summer in the northern hemisphere, growing plants absorb carbon dioxide from the atmosphere. During fall and winter, decomposing plant matter releases it back. These seasonal variations create a subtle but detectable annual rhythm in Earth's atmospheric composition, a kind of planetary breathing that reflects the presence of a global biosphere. Future telescopes might be able to detect similar patterns on exoplanets, watching for seasonal changes that could indicate the presence of life responding to changing conditions over the course of an alien year. Even more ambitiously, some researchers have proposed looking for signs of photosynthesis directly. On Earth, plants and other photosynthetic organisms absorb certain wavelengths of light for energy, while reflecting others. This creates a distinctive spectral signature called the red edge, a sharp increase in reflectance at near-infrared wavelengths that corresponds to the wavelengths that chlorophyll doesn't use for photosynthesis. The red edge is one of Earth's most distinctive features when viewed from space, and it might be detectable on exoplanets if they host vegetation that uses similar photosynthetic processes. But alien plants might have evolved to use different parts of the electromagnetic spectrum for photosynthesis, especially around stars that emit most of their energy at different wavelengths than our Sun. Around red-dwarf stars, for instance, plants might have evolved to use infrared radiation for photosynthesis, creating a different kind of spectral signature than Earth's vegetation. On worlds orbiting hotter, bluer stars, vegetation might reflect different wavelengths to avoid absorbing too much energy from their more energetic parent star. The possibility of detecting artificial light on the night sides of exoplanets has captured the imagination of both scientists and the public. Earth's night side glows with the artificial light of our cities, and this glow would theoretically be detectable from space with sufficiently sensitive instruments. If other technological civilizations exist and have developed artificial lighting, they might reveal their presence through similar night-side illumination. But detecting such artificial light would be extraordinarily challenging with current technology. The glow would be incredibly faint compared to the brightness of the planet's parent star, and it would be easily overwhelmed by natural sources of infrared radiation from the planet's warm surface. Future telescopes, designed specifically for direct imaging of exoplanets, might eventually have the sensitivity needed for such detections, but we're still decades away from that capability. Perhaps more feasibly, we might be able to detect large-scale engineering projects that could alter a planet's observable characteristics. A civilization that built massive solar collectors or orbital structures might create detectable changes in the amount of starlight that reaches their planet. Such technosignatures would be among the most definitive evidence possible for the existence of intelligent life beyond Earth. The search for biosignatures and technosignatures represents one of the most profound scientific endeavors in human history. We're not just looking for evidence of life, we're trying to understand our place in a universe that might be teeming with living worlds, each one conducting its own experiments in biology, chemistry, and perhaps even technology. Recent advances in machine learning and artificial intelligence are beginning to accelerate this search in remarkable ways. Algorithms can now sift through vast databases of exoplanet observations, looking for subtle patterns that might indicate the presence of life. These AI systems can detect correlations and anomalies in atmospheric data that human researchers might miss, potentially identifying biosignatures in datasets that have already been collected but not fully analyzed. The European Space Agency's upcoming Plato mission will monitor hundreds of thousands of stars simultaneously, looking for transiting planets and analyzing their atmospheric compositions. The sheer volume of data that such missions will generate is staggering, far more than human researchers could analyze manually. Machine learning algorithms will be essential for processing this information and identifying the most promising candidates for detailed follow-up study. NASA's planned Habitable Worlds Observatory, still in early development, is designed specifically to directly image Earth-sized planets in the habitable zones of nearby stars. This observatory would be capable of analyzing the atmospheric composition of potentially habitable worlds with unprecedented precision, searching for the combination of gases that might indicate the presence of life. But even with these advanced instruments, the search for life beyond Earth will require patience and careful analysis. False positives are always possible. Geological processes can sometimes mimic biological ones, and unusual atmospheric chemistry doesn't necessarily indicate the presence of life. Confirming that we've actually detected signs of alien life will require multiple independent observations and a thorough understanding of all the possible non-biological explanations for what we observe. The statistical approach to searching for life has become increasingly sophisticated as our catalogue of exoplanets has grown. Rather than looking for individual smoking guns, researchers are beginning to analyze populations of planets to look for patterns that might indicate biological processes operating on a galactic scale. If life is common in the universe, there might be statistical signatures that emerge when we analyze hundreds or thousands of exoplanet atmospheres. Certain combinations of gases might be more common than we would expect from purely geological processes, or there might be correlations between planetary characteristics and atmospheric composition that point to biological influences. This population-level approach to astrobiology represents a new frontier in the search for life. Instead of asking whether any individual planet shows signs of life, we're beginning to ask whether life leaves detectable fingerprints in the overall statistics of planetary atmospheres throughout the galaxy. As we continue to refine our techniques for detecting and analyzing exoplanet atmospheres, we're also developing a more nuanced understanding of habitability itself. The traditional concept of the habitable zone, that narrow range of orbital distances where liquid water might exist on a planet's surface, is giving way to a more complex picture that takes into account atmospheric composition, stellar activity, planetary geology, and a host of other factors. Some planets that orbit outside the traditional habitable zone might still harbour life in subsurface oceans, kept liquid by tidal heating or radioactive decay. Others that orbit within the habitable zone might be completely sterile due to atmospheric loss, lack of a magnetic field, or other factors that make their surfaces hostile to life. The search for life beyond Earth has become one of the most interdisciplinary endeavours in modern science, bringing together astronomers, biologists, geologists, atmospheric scientists, and even computer scientists and engineers. Each new discovery adds another piece to the puzzle, bringing us closer to answering the fundamental question of whether we are alone in the universe. The possibility that we might detect signs of life on an exoplanet within the next few decades is no longer science fiction. It's a realistic scientific goal driven by rapidly advancing technology and our growing understanding of how to recognize life's signatures across interstellar distances. Whether that life turns out to be microbial organisms in the atmosphere of a distant world, complex ecosystems on a planet orbiting a nearby star, or even technological civilizations that have altered their planet's observable characteristics, the discovery would represent one of the most profound moments in human history. It would tell us that life is not unique to Earth, that the universe might be filled with living worlds, each one writing its own chapter in the cosmic story of biology and evolution. And it would transform our understanding of our place in that story, from lonely inhabitants of the only known living world to members of a vast community of life that spans the galaxy. As the night deepens around you, and these thoughts of distant worlds drift through your consciousness, remember that somewhere out there, under alien skies we're only beginning to glimpse, the ancient dance of life and chemistry continues. Whether in forms we recognize or in ways we've never imagined, life might be stirring, growing, and evolving on worlds that are just now coming into focus through our most powerful telescopes. The search continues with patient determination, driven by the simple but profound hope that we might not be alone. And with each new world we discover, with each new technique we develop for reading the whispers of distant atmospheres, we move a little closer to finding out. The universe has already surprised us with its creativity in building planets. Perhaps it will surprise us even more with its ingenuity in nurturing life. The instruments we use to peer into these distant worlds are marvels of engineering that would have seemed like magic to astronomers just a few generations ago. The precision required to detect the subtle changes in starlight caused by a transiting planet is almost incomprehensible. We're measuring variations in brightness, equivalent to detecting the shadow of a coin passing in front of a coin passing lighthouse from hundreds of miles away. Consider the challenges involved in direct imaging of exoplanets, actually photographing these distant worlds rather than inferring their presence through indirect methods. The contrast between a bright star and its much dimmer planetary companions is staggering. It's roughly equivalent to trying to spot a candle flame while standing next to a blazing searchlight, except the searchlight is millions of times brighter than the candle, and they're separated by distances measured in astronomical units. To overcome this challenge, astronomers have developed ingenious techniques that seem almost like sleight of hand. Coronagraphs block out the overwhelming light of the parent star, creating an artificial eclipse that allows the much fainter light of orbiting planets to become visible. Adaptive optics systems correct for the blurring effects of Earth's atmosphere in real time, using deformable mirrors that adjust their shape hundreds of times per second to compensate for atmospheric turbulence. The results of these technological achievements are nothing short of remarkable. We now have actual photographs of exoplanets, tiny points of light that represent entire alien worlds orbiting distant stars. These images might not reveal surface details or geographic features, but they contain a wealth of information about planetary temperatures, atmospheric composition, and orbital characteristics. Each photon of light captured in these images has travelled across vast stretches of interstellar space, carrying with it the encoded story of the world that reflected or emitted it. By analysing the spectrum of this ancient light, astronomers can determine what gases exist in alien atmospheres, what temperatures prevail on distant surfaces, and even how weather patterns might distribute heat and moisture across these far-off worlds. The upcoming generation of space telescopes promises to revolutionize our ability to study exoplanets in unprecedented detail. These observatories will be equipped with instruments so sensitive they could detect the thermal glow of a human body from the distance of the moon, and so precise they could measure changes in stellar brightness equivalent to a single LED light being turned on and off in Times Square. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2022, will use a technique called gravitational microlensing to discover thousands of new exoplanets, including many that would be impossible to detect with current methods. When a star passes precisely in front of a more distant star from our perspective, its gravity acts like a natural magnifying glass, briefly brightening the background star's light. If the foreground star has planets, they create additional brightening events that reveal their presence and characteristics. This technique is particularly sensitive to planets that orbit far from their stars' worlds that might be more similar to Jupiter or Saturn in our own solar system. By combining microlensing discoveries with the close-in planets found by transit surveys, we're building a complete census of planetary systems throughout our galactic neighborhood. The extremely large telescopes now under construction on Earth will have mirrors 30 to 40 meters across, large enough to park a small airplane on their surfaces. These titanic instruments will be capable of directly imaging Earth-sized planets around nearby stars and analyzing their atmospheres for signs of water, vapor, oxygen, and other gases that might indicate habitability or even biological activity. Imagine standing on the summit of a mountain in Chile or Hawaii, looking through one of these colossal telescopes as it captures the faint light of an alien world. That tiny speck of reflected starlight might be bouncing off clouds in an alien sky, or glinting from the surface of an extraterrestrial ocean. The photons entering the telescope might have last interacted with matter on a world where strange life forms are going about their daily existence under the light of a foreign sun. The data analysis techniques used to extract information from exoplanet observations have become increasingly sophisticated. Machine learning algorithms can now detect subtle patterns in stellar brightness that human astronomers might miss, identifying planetary transits buried in the noise of stellar variability and instrumental effects. These artificial intelligence systems can process vast amounts of observational data in minutes or hours, searching for the telltale signatures of worlds that might have taken human researchers months or years to discover. But perhaps the most exciting developments are happening in the realm of atmospheric characterization, our ability to determine what gases exist in the skies of distant worlds. The James Webb Space Telescope has already demonstrated remarkable capabilities in this area, revealing the atmospheric compositions of exoplanets with a precision that seemed impossible just a few years ago. The process is elegantly simple in concept but fiendishly difficult in execution. When a planet transits across its star, a tiny fraction of starlight passes through the planet's atmosphere before reaching Earth. Different gases absorb light at specific wavelengths, creating a unique spectroscopic fingerprint that reveals the atmospheric composition. It's like reading the chemical recipe of an alien world written in the language of starlight. Recent observations have revealed exoplanet atmospheres containing water vapor, carbon dioxide, methane, and even more exotic compounds like titanium oxide and vanadium oxide. Some worlds have clouds made of silicates, essentially floating particles of sand and glass. Others have atmospheric chemistry so alien that we're still trying to understand how such compositions could arise or remain stable over geological time. The hunt for biosignatures in exoplanet atmospheres represents one of the most technically challenging endeavors in modern astronomy. The gases produced by life are often present in tiny concentrations, creating spectral signatures that are incredibly difficult to detect above the noise of instrumental limitations and stellar variability. It's like trying to hear a whispered conversation in a crowded restaurant while standing outside in a thunderstorm. Yet the potential payoff is so profound that astronomers are pushing the boundaries of what's technically possible. Future missions are being designed with the specific goal of detecting Earth-like biosignatures around nearby stars, combinations of gases like oxygen and water vapor that would be difficult to explain without biological processes. The search is also expanding beyond simple gas detection to look for more subtle signs of life. Seasonal variations in atmospheric composition might indicate biological cycles, similar to the way Earth's atmosphere changes as plants grow and die back over the course of each year. Unusual chemical disequilibria might suggest active biological processes maintaining unstable atmospheric compositions. Some researchers are even exploring the possibility of detecting the spectral signature of photosynthesis itself, the distinctive way that plant-like organisms might reflect certain wavelengths of light while absorbing others. Energy. On Earth, vegetation creates a sharp increase in reflectance at near-infrared wavelengths called the red edge, which might be detectable on exoplanets if they host photosynthetic life. The challenges are immense, but so are the potential rewards. The detection of genuine biosignatures in an exoplanet atmosphere would represent one of the most significant discoveries in the history of science, fundamentally changing our understanding of life's prevalence in the universe and our own cosmic significance. As we push deeper into this golden age of exoplanet discovery, we're also grappling with profound questions about the nature of life itself. The diversity of worlds we've discovered has forced us to expand our definition of habitability far beyond the narrow, Earth-centric view we once held. Life might exist in forms and environments we've never imagined, thriving under conditions that would be instantly lethal to terrestrial organisms. The subsurface oceans of icy moons in our own solar system have already shown us that life might flourish in environments completely cut off from sunlight, sustained instead by chemical energy from geological processes. If such conditions exist on exoplanets, perhaps in the form of rogue worlds drifting between stars, warmed only by radioactive decay in their cores, then the number of potentially habitable environments in the galaxy might be far larger than we've ever dared hope. The search for exoplanets has also revealed the dynamic nature of planetary systems over cosmic time. Worlds migrate inward and outward from their birth locations. They exchange atmospheres through impacts and gravitational interactions. Some get ejected from their systems entirely, becoming solitary wanderers in the cosmic deep. This dynamical evolution means that habitability itself might be a moving target. A world that starts life as a frozen ice ball might migrate into its star's habitable zone and develop temperate conditions over millions of years. Conversely, a planet that begins with Earth-like conditions might be pushed into a more distant orbit, where its oceans freeze solid. The implications for life are profound. Evolution might have to be remarkably adaptable to survive the changing conditions as worlds migrate through different temperature regimes. Alternatively, life might be more robust than we imagine, capable of surviving in dormant states during unfavorable periods and reactivating when conditions improve. Some of the most intriguing discoveries have come from studying planets in multiple star systems, where the complex gravitational interactions create orbital dynamics unlike anything in our solar system. Planets that orbit both members of a binary star system would experience double sunrises and sunsets, with complex seasonal patterns as the two stars move through their own orbital dance. The climate modeling for such worlds pushes our understanding to its limits. How would atmospheric circulation patterns develop on a planet heated by two stars of different colors and temperatures? What would the seasonal cycles be like as the planet's distance from each star varied over the course of its orbit? These questions require new approaches to planetary science, expanding our models beyond the single star systems we're familiar with. The discovery of circumbinary planets worlds that orbit both stars in a binary system has been one of the most cinematically inspiring developments in exoplanet science. These are the real-world equivalents of Luke Skywalker's fictional homeworld Tatooine, complete with double sunsets and complex seasonal patterns, driven by the orbital mechanics of multiple stellar companions. But the reality of such worlds might be even stranger than fiction. The gravitational environment around binary stars creates regions of orbital stability and instability that shift over time as the stars themselves orbit each other. Planets in these systems might experience periods of relatively stable climate, interrupted by intervals of dramatic heating or cooling, as their orbits become perturbed by the complex gravitational environment. As our catalogue of exoplanets has grown, we've also begun to identify patterns in how different types of planetary systems form and evolve. The architecture of our own solar system, with small rocky planets close to the Sun and large gas giants farther out, appears to be just one of many possible configurations. Some systems have their largest planets orbiting very close to their stars, with smaller worlds scattered throughout the outer regions. Others show evidence of dramatic migration events that have completely reshuffled the original planetary arrangement. A few systems appear to be in the process of ongoing evolution, with planets still migrating and interacting gravitationally in ways that will continue to reshape the system's architecture over millions of years. The study of planetary system architecture has revealed that the formation of planets is a far messier and more chaotic process than early theoretical models suggested. Computer simulations of planetary formation now include complex interactions between forming planets and the disks of gas and dust from which they condense, leading to scenarios where worlds can migrate vast distances from their birthplaces. This new understanding has important implications for habitability. A world that forms in the outer reaches of its system, where water can freeze into ice and contribute to planetary growth, might later migrate inward to become a temperate, potentially habitable world. The migration process itself might help explain why we see so many planets in configurations that don't match our solar system's architecture. The chemical composition of exoplanets has also provided insights into the formation history of different stellar systems. Planets that formed around metal-rich stars, stars with higher concentrations of elements heavier than hydrogen and helium, tend to have different characteristics than those that formed around metal-poor stars. This chemical connection between stars and their planetary companions helps us understand how the galaxy's chemical evolution has influenced the types of worlds that form around different generations of stars. Some of the oldest stars in our galaxy, which formed when the universe was much younger and contained fewer heavy elements, might host planetary systems with very different compositions than the worlds we're familiar with. These ancient systems could contain planets made primarily of hydrogen, helium, and the light elements that dominated the early universe, creating worlds with properties we can barely imagine. Conversely, planets forming today around young, metal-rich stars might be incredibly diverse in their compositions, incorporating complex mixtures of elements that weren't available when older planetary systems formed. The chemical evolution of the galaxy over cosmic time has gradually enriched the interstellar medium with heavy elements produced by successive generations of stars, providing the raw materials for increasingly complex planetary compositions. The search for potentially habitable worlds has also led to a deeper appreciation of the role that stellar activity plays in shaping planetary atmospheres over time. Young stars tend to be much more active than older ones, producing powerful flares and stellar winds that can strip away planetary atmospheres or alter their chemical composition through high-energy radiation. This creates a complex relationship between stellar age and planetary habitability. Very young systems might be too violent for stable atmospheric conditions, while very old systems might have planets that have lost their atmospheres entirely over billions of years of stellar evolution. There might be a sweet spot in stellar age where conditions are just right for long-term atmospheric stability and the development of complex chemistry. The study of how stellar activity affects planetary atmospheres has become increasingly important, as we've discovered that many potentially habitable exoplanets orbit red dwarf stars, which can remain active for much longer periods than Sun-like stars. Understanding whether planets around such stars can maintain stable atmospheres over geological time is crucial for assessing their potential for hosting life. Recent research has suggested that planets with strong magnetic fields might be able to protect their atmospheres from stellar wind erosion, while those without magnetic protection might gradually lose their gaseous envelopes to space. This adds another factor to the complex equation of habitability, not just the right temperature and chemical composition, but also the presence of a magnetic field strong enough to shield the atmosphere from its host star's radiation. As you drift toward the peaceful realm of sleep, let these thoughts of distant worlds and cosmic possibilities settle gently in your consciousness like stardust on a quiet night. The universe we've discovered through our search for exoplanets is far stranger, more diverse, and more wonderful than we ever dared imagine when we first began pointing our instruments toward distant stars. From tidally locked worlds where one side experiences eternal day while the other remains frozen in perpetual night, to diamond planets where the very ground might be made of crystallized carbon compressed by unimaginable forces, the gallery of exoplanets continues to challenge our assumptions about what's possible in the cosmic laboratory of planetary formation. Water worlds covered by oceans hundreds of kilometers deep harbor possibilities for life in environments that have no analog on Earth. Super-Earths with crushing gravity and thick atmospheres might support exotic chemistries that could give rise to forms of life we've never contemplated. And somewhere among the thousands of worlds we've already discovered, there might be planets so similar to Earth that standing on their surfaces would feel almost like home. The techniques we've developed for finding and studying these distant worlds represent some of humanity's most ingenious achievements in the art of cosmic detective work. With nothing more than the subtle variations in starlight and the patient application of physical laws, we've learned to read the stories written in the atmospheres of planets hundreds of light years away. We've discovered that planets are not rare cosmic accidents, but appear to be the natural, inevitable result of star formation. Nearly every star we've studied in sufficient detail seems to host at least one world, and many harbor entire families of planets with diverse characteristics and complex orbital relationships. This revelation has profound implications for our understanding of our place in the universe. If planets are common, and if some fraction of those planets exist under conditions suitable for life, then the cosmos might be teeming with living worlds, each conducting its own experiments in biology, chemistry, and evolution. The next few decades promise to bring discoveries that could fundamentally change how we see ourselves and our cosmic significance. The James Webb Space Telescope is already revolutionizing our understanding of exoplanet atmospheres, while future observatories designed specifically for exoplanet research will push our capabilities even further. We may be on the verge of detecting the first definitive biosignatures in the atmosphere of a distant world, chemical evidence that life exists beyond our solar system. Such a discovery would rank among the most profound in human history, telling us that we are not alone in this vast universe, but rather part of a cosmic community of life that might span the galaxy. Whether that life takes forms we recognize or manifests in ways we've never imagined, its discovery would transform our understanding of biology, evolution, and our own place in the grand story of cosmic development. It would remind us that Earth, for all its beauty and uniqueness, is just one chapter in a much larger tale of life's creativity and resilience. The search continues with patient determination, driven by instruments of extraordinary sensitivity and the simple but profound desire to know whether we share this cosmos with others. Every new world we discover adds another verse to the cosmic poem of planetary formation. Every new technique we develop for studying distant atmospheres brings us closer to reading the chemical signatures that might reveal life's presence among the stars. And as the gentle rhythm of discovery continues, as new planets are announced and their characteristics slowly revealed through careful observation and analysis, we're reminded that we live in an age of exploration, as remarkable as any in human history. We are the first generation to know with certainty that other worlds exist, the first to glimpse the incredible diversity of planetary systems throughout the galaxy, and perhaps the first to find evidence that life itself might be a cosmic commonplace rather than a terrestrial rarity. The universe has already surprised us with its creativity in building worlds. Perhaps it will surprise us even more with its ingenuity in nurturing life. And somewhere out there, under alien skies painted with unfamiliar constellations, the ancient dance of chemistry and evolution continues, writing new chapters in the ever-expanding story of life in the cosmos. The search for exoplanets has become humanity's greatest detective story, written in whispers of starlight and decoded through instruments of impossible precision. As we drift toward the end of our cosmic journey tonight, it's worth pausing to appreciate just how far we've traveled, not just in our exploration of distant worlds, but in our understanding of what it means to search for life itself. When the first exoplanet was confirmed around a sun-like star in 1995, we had no idea we were opening a door to a universe far more populated and diverse than we'd ever imagined. That single world, 51 Pegasi b, was just the first note in what has become a symphony of discovery spanning nearly 3 decades. From that humble beginning, we've catalogued thousands upon thousands of worlds, each one adding its own unique voice to the cosmic chorus. The sheer variety of what we've found continues to astonish even the astronomers making the discoveries. There are planets where diamond rain might fall from crystalline clouds, worlds where the very air would crush you instantly, and others where gentle breezes might carry the scent of alien flowers across continents we'll never see. Some orbit so close to their stars that their surfaces glow like embers, while others drift in the cold darkness between stars, warmed only by the slow decay of radioactive elements in their cores. But perhaps the most remarkable aspect of this golden age of discovery isn't the exotic nature of the worlds we've found. It's how they've transformed our perspective on what's normal in the universe. Our solar system, with its orderly arrangement of small rocky planets near the sun and large gas giants farther out, now appears to be somewhat unusual. The typical planetary system looks nothing like our familiar cosmic neighborhood. Instead, the galaxy seems to prefer super-Earth's worlds, larger than our planet, but smaller than Neptune, existing in a size range that our solar system completely lacks. These mysterious worlds might be ocean planets covered by seas deeper than any on Earth, or they could be rocky worlds with crushing gravity and atmospheres so thick they create permanent greenhouse effects. We simply don't know, because we have no local examples to study. This realization has been both humbling and exciting. It suggests that the universe is far more creative in building worlds than our limited earthly perspective allowed us to imagine. Every assumption we made about planet formation based on studying our own solar system has been challenged by the incredible diversity of exoplanetary systems we've discovered. The techniques we've developed to find these distant worlds represent some of the most ingenious problem-solving in the history of science. The precision required to detect a planet transiting across a distant star is almost incomprehensible. We're measuring changes in brightness so subtle that they would be completely overwhelmed by the twinkling caused by Earth's atmosphere. Yet we've learned to read these faint whispers from space with such accuracy that we can determine not just a planet's size and orbital period, but also the composition of its atmosphere and even the weather patterns in its alien skies. The radial-velocity method, which detects the tiny wobble a planet causes in its star's motion, requires measuring velocity changes smaller than a human walking pace from distances of hundreds of light years. It's like detecting whether someone on the other side of the world is speeding up or slowing down by a single step, using only the sound of their footsteps carried on the wind. These remarkable achievements in cosmic detective work have revealed a universe where planets are not rare cosmic accidents, but appear to be the natural outcome of star formation. Nearly every star we've studied seems to host at least one world, suggesting that our galaxy contains hundreds of billions of planets, more worlds than there are people who have ever lived on Earth. Among this vast population of alien worlds, some must surely harbour conditions suitable for life. The mathematics of probability makes this almost inevitable. Even if only a tiny fraction of planets develop the right combination of temperature, atmospheric composition, and chemical ingredients, the sheer number of worlds means that potentially habitable planets could number in the billions. The search for signs of life itself has become increasingly sophisticated as our instruments have grown more sensitive. The James Webb Space Telescope can now analyze the chemical composition of exoplanet atmospheres with extraordinary precision, detecting water vapor, carbon dioxide, and other gases that might indicate habitability. Future observatories will push these capabilities even further, potentially allowing us to detect the subtle chemical signatures that life leaves in planetary atmospheres. The possibility that we might find definitive evidence of life beyond Earth within the next few decades is no longer science fiction. It's a realistic goal driven by rapidly advancing technology and our growing understanding of how to recognize life's fingerprints across interstellar distances. Such a discovery would represent one of the most profound moments in human history, fundamentally changing our understanding of our place in the universe. But even if we never find conclusive signs of extraterrestrial life, the search for exoplanets has already transformed our cosmic perspective in ways both subtle and profound. We now know that we live in a universe where worlds are commonplace, where the raw materials for planet formation are scattered throughout the galaxy, and where the conditions necessary for complex chemistry and potentially life might be far more widespread than we ever dared hope. The story of exoplanet discovery is also a testament to human curiosity and persistence. For decades, astronomers pursued these invisible worlds with instruments barely sensitive enough to detect them, driven by nothing more than the conviction that other worlds must exist and the determination to find them. Their patience and ingenuity have given us a gift of immeasurable value, the knowledge that Earth is not alone in harbouring worlds, that our solar system is part of a vast community of planetary systems spanning the galaxy. As we continue to refine our techniques and build more powerful telescopes, the pace of discovery shows no signs of slowing. Every week brings announcements of new worlds, new atmospheric compositions, new orbital configurations that challenge our understanding of how planets form and evolve. We're still in the early chapters of this story, with most of the galaxy's planets yet to be discovered and characterized. The children growing up today will inherit a universe far richer and more diverse than the one we knew just a generation ago. They'll grow up knowing that planets are everywhere, that alien sunsets paint foreign skies every evening, and that somewhere among the thousands of worlds we've already found, there might just be another pale blue dot harbouring its own extraordinary story of life and evolution. This transformation in our cosmic perspective has happened gradually, world by world, discovery by discovery, but its cumulative impact has been revolutionary. We are no longer inhabitants of the only known planetary system, wondering whether other worlds exist. We are citizens of a galaxy that we now know is teeming with planets, each one a unique experiment in the physics and chemistry of world building. The universe has revealed itself to be stranger, more creative, and more wonderful than we ever imagined. And as we drift towards sleep tonight, let that knowledge settle gently in your consciousness, like starlight through a window. Somewhere out there, under alien constellations we've never seen, worlds are spinning quietly in the darkness, carrying their own stories of formation, evolution, and perhaps even life. The journey we've taken tonight through the gallery of alien worlds reminds us of something both humbling and beautiful. We are cosmic citizens in the truest sense. Every atom in your body, every element that makes up the very thoughts drifting through your mind right now, was forged in the nuclear furnaces of ancient stars that lived and died billions of years before our sun was even born. Those same stellar nurseries that created the building blocks of life on Earth are still at work throughout the galaxy, enriching the cosmos with the heavy elements necessary for rocky planets, complex chemistry, and perhaps biology itself. The carbon in your cells, the oxygen you breathe, the iron in your blood, all of it is stardust, scattered across space by stellar winds and supernova explosions, eventually finding its way into new worlds, orbiting distant suns. This cosmic recycling means that we share a deep kinship with every exoplanet we've discovered. The super-Earths orbiting red-dwarf stars, the scorching hot Jupiters locked in tight embraces with their parent stars, the lonely rogue planets drifting through interstellar space. They're all made from the same cosmic ingredients, shaped by the same fundamental forces of gravity and time. Perhaps that's why the search for exoplanets feels so deeply meaningful. We're not just looking for alien worlds, we're searching for family, for distant cousins in the grand tree of cosmic evolution. Every planet we discover is a reminder that the universe is not a cold, empty void punctuated by rare oases of matter. Instead, it's a living, breathing cosmos where world-building is as natural and inevitable as the tides. As our techniques become more refined and our instruments more sensitive, we're beginning to glimpse not just the existence of these distant worlds, but their personalities. Some planets have thick, steamy atmospheres that trap heat like cosmic greenhouses. Others are windswept and barren, their thin air sculpted by stellar radiation. Still others might have weather patterns so complex they dwarf anything we see on Earth, global storm systems that persist for centuries, or seasonal cycles driven by the intricate dance of multiple suns. The quiet revolution in our understanding continues with each passing night. Right now, as you settle into the peaceful embrace of sleep, telescopes around the world and in space are patiently watching distant stars, waiting for the telltale dimming that signals another world crossing in front of its sun. Data is flowing from space-based observatories, carrying the encoded stories of atmospheres we've never breathed and surfaces we've never touched. And in laboratories and universities across our own world, researchers are developing the next generation of instruments that will push our cosmic vision even further. They're designing telescopes that could directly image Earth-like planets around nearby stars, observatories that could detect the seasonal changes in alien atmospheres, and spectrographs sensitive enough to identify the chemical signatures of life itself. The future holds possibilities that would have seemed impossible just decades ago. We might witness the first confirmed detection of an exoplanet, with an atmosphere rich in oxygen and water vapor, the kind of chemical combination that would be difficult to explain without photosynthetic life. We might discover worlds where the very air shimmers with organic compounds, planets where biology has painted the landscape in colors we've never seen, or perhaps the universe will surprise us in ways we haven't yet learned to imagine. Maybe life takes forms so different from terrestrial biology that we'll need to expand our very definition of what it means to be alive. The cosmos has already shown us its remarkable creativity in building worlds. Who knows what ingenuity it might display in nurturing life. Tonight, as you drift toward dreams, carry with you the gentle knowledge that you are part of something vast and wonderful. The same curiosity that drives you to wonder about distant worlds, the same capacity for awe that makes you marvel at alien sunsets. You'll never see these qualities connect you to every explorer who has ever gazed up at the stars and asked, what else is out there? The search for exoplanets is really the search for ourselves, for our place in the cosmic story, for our significance in a universe that grows larger and stranger with each new discovery. And what we found is both humbling and inspiring. We are small, yes, but we are part of something unimaginably grand. We are rare, perhaps, but we are not alone in harbouring worlds. The universe is vast, patient, and filled with more wonders than we can count. And we're just beginning to explore it, one distant world at a time, one whisper of starlight at a time, one peaceful night of dreaming at a time. Sleep well, fellow traveller. The stars are waiting, and tomorrow there will be new worlds to discover.